Okay, hi everyone. I hope that you are doing well. And today we have the lecture number 5. From previous lecture, you remember that our great main was modeling the dynamic of a financial market. But what does it mean? What assumption we need to do? The assumption are that the market consists of at least three components. The first component, it is riskless asset. The second, risky asset, and the third, derivative security. It is like opportunities for investor. Investor can input your money on the bank account, and it is a riskless asset. Can trade by risky asset, for example, stock, and can trade derivative securities. In our case, it will be European options. Okay. How to model riskless asset? It is clear. And in this case, the amount of money, for example, which you put on your bank account, depends on only time. And we assume that doesn't depend on a random factor. And we assume that R is analyzed interest rate, continuously compounded, and it is constant and doesn't depend from operation. It is deposit operation or borrowing operation. So with this, everything is clear. The second component is risky asset. And for risky asset, we suppose maybe Brownian motion, it's like chaotically motion, is a basic process. And maybe diffusion is a suitable process. Do you remember what is Brownian motion? I can refresh your memories. It is the stochastic process which had the next properties. At the initial moment, the value of process is 0. This process is almost surely continuous, has independent and stationary increments, and that these increments has normal distribution, and parameters of this normal distribution is 0 and u, where u is a distance between two values. It is 4 main properties which defined a Brownian motion, but there are additional properties such as that Wiener process is Markov process, it is martingale, and it is fractal with Hurst coefficient is half. Okay. So we would like to model stock prices, not like just this Brownian motion, because it is like Brownian motion describes chaotical behavior of particles, yes, but we would like to have a deformation of this Brownian motion, because you see, you know that the stock prices has trend, for example, yes, volatility, and for this we choose the diffusion process. It is 1.5, yes, you see, or it's called Ito processes. So it is the same, diffusion process and Ito process in our framework. What is diffusion process? Diffusion process, it is like deformation, yes, of this Wiener process, and it can be written in this form and have coefficient 8 and B. It is drift coefficient and diffusion coefficient, And the meaning of this coefficient is very important for us. But before, I would like to note what is differential from WT. WT. It is very important, essential for us. It is we can this write like epsilon square root from dt, where epsilon it is small Wiener noise, white noise, and it is it has normal distribution, standard normal distribution with means 0 and variance 1. So according definition of this iter process, this coefficient have simple meaning, and it is like shift for the shift of the first order, average shift for the first order. If we have this infinitely close interval delta t, it is coefficient a xt, and the shift of the second order, it is variance. It is this function b square. But the shift of the higher power equals 0. Okay, and we know already some example of iter processes. For example, Ornstein-Uhlenbeck process, and you see that it is like process 1.5, but the coefficient before dt, it is coefficient a from xt. It is this product coefficient b, it is like constant sigma, it is coefficient before db, yes? And arithmetical Brownian motion and geometrical Brownian motion. Geometrical Brownian motion, it is very convenient and very important for us, and it is coefficient R. In this case, it is product mu and xt, and coefficient B product sigma and xt. What is from an economical point of view? Maybe geometrical Brownian motion, it is like suitable model. Really, if we consider, I want to take a pen. If we consider the change in the stock price, it is DD. It's like rate of change, speed of change. Yes, it is from economical point of view, it is proportional by mu and s. And maybe you remember the similar equation in the lecture 1. And the solution of this ds divided by s, we can write and multiply the both sides by dt, and after that integrate. So the solution, it is that. But the standard deviation of the change in a short period of time should be proportional to the stock price, and leads to this model. So ds, no, multiplied by dt, mu s dt, and plus sigma s dz. So it is term defines a trend, and it is that the stochastic term. Okay. Clear. And for example, if we have the parameter sigma volatility and mu expected rate from historical data, and we know that the process for a stock price we can write in this way. Why? It is no like this, ds divided by s equals mu dt plus sigma dz, and we just substitute oh, I don't understand right. Geometrical, it was just substitute sigma and mu. How can we know about these parameters from historical data? It is easy. If we have the sequence of stock prices, it is like time series, for example, from stock prices. We can find that time series H. For example, we have Sn. It is like S0, S1, S2, and so on. We can to find Hn equals log Sn divided by Sn minus 1. And after that, if we find the mean from this, it will be mu. So mu equals mathematical expectation from Hn. But how we can estimate of mathematical expectation? It's mean. Mean, it is like sum divided by the amount of this member. Yes. So it is how we can find expected rate from historical data. But volatility is easy too. It is like no mathematical expectation, but square root from variance. But if we find sigma, I write this like square root from variance, it will be just days volatility from one day, volatility from one day. But if we would like to find just volatility, it is volatility for 1 year. So we need to multiply this by amount of working days at the year. So it is multiplied by 241. So sigma equals this daily sigma multiply by 241. Okay. And so from this example, what it gives us? Okay, we substitute this sigma and mu, and after that we can to write dz like epsilon square root from dt, and we know what is epsilon. And if we write discrete form for ds, it is delta s. So now we can substitute delta s, yes, equals s minus S0, but S0, for example, 100, and delta T, for example, 1 week. 1 week, it is in unit of years. What is this part of year? It is this part of years. So everything we substitute, and we have that the growing the stock price during this week equals 0.288, but plus this value, where value it is random variable, and with standard normal distribution. Okay. So what we have that we have found the model for risky asset. It is geometrical Brownian motion. Geometrical Brownian motion. It is like a partial case of the ITO process. So it is diffusion process from one side, and from another side, on the other side, it is a process which suits us from economical points of view. Okay, but how we can find the solution of this equation, stochastic differential equation, if it exists? And for finding solution, we need to know the ITA lemma and something else. ITA's lemma states that if we have that process is given by stochastic differential in this form, and we have some function g, function which depends on time and process xt. So the digit we can find like the process eta2 with this coefficient, no, in this form, okay? And how we can solve stochastic differential equation? It is not possible in every case, but if on the right side the function a and b, in this case it is f and s, depends on just t time, so we can find a solution in this form, but it is not always that this function from t, yes? So if it is not from t, there are some cases, I repeat, not always, when we can use lemma eta and to find function f capital in such a way that the function before dt and dz will be like function just from t. So it is 2.20, it is lemma eta for this process, and we would like that this coefficient equals ft and this coefficient equals st. So only from t. So from this we can write this equation, and from this equation, and it is the material of the last lecture, and it is the conditional which allows us to find this function. And if we find, we can solute like this. Okay, so how we can apply this for our geometrical Brownian motion? It is logarithm random walk, it doesn't matter. We can call it in one of this way. So we have this geometrical Brownian motion, you remember, Brownian motion, and function a in our case, function a in our case, it is this function, yes, it is function a, and it's function b, so we would like that it will be like in bracket function from t only, and this on t2, and it is I mentioned that it is condition how we can find this function s and phi and f, no, f literal. So we write this condition and we substitute what is b and what is a. b it is sigma x. So this if b sigma s, so if we find if we find derivatives respect to x, what it will be? So this function, it is sigma x. So the first derivatives, it will be who would like to say? Rostik.
Sigma.
Sigma, yes, thank you. Absolutely. But you see that it is the second derivatives. But the second derivatives, it is derivatives from sigma. And it will be Rostik.
1.
From constant. From 5, from 3.
0.
0, yes, okay. So you see that these derivatives equal 0. What is about the second term? It is a divided by b. A, it is mu x, yes, divided by b, sigma x, x crossed. So we have mu divided by sigma, but it's constant. So the derivatives, it is like this, 0. Okay. So in this equation, you see that a right side equals 0, on the left side, it is like product this by this, so it is not 0. So the derivatives respect to t from s equals 0. Yes, because b it is bx. Sorry, Никита Кольчик. Okay, so we have yes, no, because b it is like constant, because b it is sigma multiplied x, but we need to find derivatives respect to t. So as derivatives from t equals 0. From this we have that no, it is 0, so all this equals 0, so it is 0. And we write dot if we consider derivatives respect to time. Okay, so we have this equation, and it is understandable that it is clear that the solution of this equation will be s from t. It is what? How do you need? If the first derivative 0, it means that it was, if derivative is 0, it was what it was? Constant. Okay, so it is constant, but we can to choose any constant, and for us it is convenient to choose sigma, so it is sigma. Okay, so st equals sigma. And the equation 221, it is that df derivatives from df respect to ds equal st divided by b from xt. Okay. And if we substitute df respect to dx equals s from t, it is sigma, but b, what is b? Sigma x, sigma multiply x, sigma crossed, and we need to solve this. How we can do this to find maybe what is what is this function f that its derivative equals 1 divided by x? What is
ln
it?
n, ln
Yes,
x.
yes, you're right, absolutely. ln x, okay. So f, it is ln x. It is this. So we find this function. And according to this theory, if we choose this function ln x and substitute in this df, according to its lemma, so this function depends only from t, and this function will be depends only from t. Okay, so we can find this df according lemma eta. No, substitute all this. Yes, df, it is dln. But what is in the right side? Df, the derivatives f respect to dt. What is derivative f respect to dt?
Zero.
Zero, absolutely. Okay, so it is zero. Function a. What is function a? Remember? No? Function a. It is this. Function a, it is what before dt, mu x, and function b, sigma x, okay? So function a it is x mu df derivatives f respect to dx, it will be please, Lisa, derivatives from this.
1 divided by x.
Yes, you're right. So we have x mu multiplied 1x, so only mu, yes, x crossed only mu. So df equals mu. Okay, the second derivatives. So derivatives from this, the second derivatives. The first derivatives 1 divided by x. The second, it is derivatives from this. It will be how much?
Minus 1 divided by x squared.
Yes, you're right. Okay. So it is this derivatives equals minus a divided by x squared, but b, it is sigma s, so it will be sigma square x square divided by x square, so just just this, yes, b square. No, if you want, I would like write this plus b square. It is sigma square x square divided by 2 and 1 divided by x square with minus. So not plus, minus. It's crossed. So we have sigma squared divided by 2. Yes, it is this. And plus b, we write sigma s, sigma x, and first derivatives, it's 1 divided by x, 1 divided by x. So only sigma remains, yes? Sigma dz. Okay. So we obtained this equation, and now we need to integrate left and right sides from 0, no, for example, to t capital, where t is time to maturity. So integral from d and some function, it will be this function ln xt, and we have that it is down limit 0 and it is up limit t. So we substitute instead t ln xt minus ln x0. Okay, it's clear? Okay, right side. It is like coefficient constant because it is integral respect to dt, so it's constant. And integral from dt, it is just t. And from 0 to t, it is t minus 0 and just t capital. And what is this? It is integral eta. It is integral where we have the stochastic differential, and we agree that this integral means just random changes, and we can write this like this value. So this integral we can write like this value. It is like dz t minus dz0, and we can write this in this way. So we have the solution, or xt, if the t is time to maturity, or we can substitute any t, any time, but it doesn't matter. And so we have that the solution of the geometrical Brownian motion, which was given like the stochastic differential equation, it is has 4 to 25. So it's our solution. And what is interesting, why we have chosen exactly the geometrical Brownian motion, but not arithmetical Brownian motion. Maybe someone knows, I don't know, but because into the negative area x less 0, the random walk in the Wiener process, it is impossible for the logarithmic model. This property is indeed expected from the form. No, okay. So it means that the value of geometrical Brownian motion always positive. But if we consider arithmetical Brownian motion, the value can be negative, and it is not very well for economical applying. Okay. Um, so, and now we know the two components. The first component, the riskless asset, we know how to model this. We know the geometrical Brownian motion and solution, like 225 for model risky asset, for example, stocks. And now we would like to find the fair price for derivatives. And this moment, I would like to say that the result now is known like the model, the Black-Scholes model. But Black and Scholes, they found this result in other way than I am going to show you. And the next on the next lecture we will know this way. But today I would like to mention the other way. It is modern way when we can define fair price of derivatives like the present value of the expected payoff at maturity. Okay, so again now our task, our aim, to find fair price of derivatives. It is like premium on the site. Yes, you remember how much cost, for example, call option with given parameters, with given time to maturity, and with fixed other parameters. And to find a fair price, we use the definition that it is like expected payoff at maturity, but maturity in the future. But we now at the present moment, for example, okay, for example, let's repeat, it is like material of the first lecture. For example, today we have this 100 stock price, and we don't know, and it's moment T, moment maturity. We don't know if we now at this point, if we now at this point, we don't know it will be more than this or less, and we are not sure at anything. But we choose the strike price, K, strike price. And if at the time of maturity, this market price more than this strike price, so this difference, it is our profit. Do you remember this? Yes? It is from the first lecture. S minus K. S minus K is called payoff function. Is called payoff function. So if today, for example, 100, and we choose K 110, but at the time T market price at 150 minus 110, so it is 40 euros, for example. It's our profit. It's our profit. Okay, but its profit we will get at this time. But what is the price of this profit for today? Can you find this? What we need to do? How we can to find present value? Present value of this. Present value. What is present value? It is problem set 1. Lisa, do you remember present value? If we need this profit, payoff function, F, just like F, Lisa? No, yes. Rostik. What is present value of for your
I
function?
don't really remember. It's like a future value plus something.
It is like future value?
Plus,
No, no
plus,
plus,
no,
no
no.
plus. Okay, what is logic? What is logic? If, for example, it is 40 euros, yes, S minus K,
Yes.
40 years. But if now we put 40 years on the bank account and the rate is R, so for this time T, it will be how much? 40 euros. So I would like future values. For example, future values. Maybe you forget present values, but remember future values. Future values. For example, we have this F today, but on the future, it will be how much? If the rate, interest rate are
1 plus R in
yes, 1 plus R
and
no, time T, yes?
yes.
Yes, okay. So we repeat what is future value, but what is present value? Present value, it is like the operation opposite. It is this we have future value, but present value,
Yes.
How we can, it is future value. And what we need to do is future value. Future value, it is this, but F, it is present value. It is present value, yes? Future value equals present value multiplied 1 plus R to the power t. So present value, it is future value.
Divide by
Yes.
1 plus RT.
You're right. Thank you. So we repeat what is present value. Present value. Okay. The second moment, it is that S minus K, it is like 150 minus 110. It is for this concrete trajectory, yes? But maybe other trajectory, we don't know what is this trajectory. So we need to find this like mathematical expectation of this all value, yes? Because maybe this value, this value, this value. So we need to take into account all these trajectories. So it is the fair price. It is this. It is we need to write future value divided by this. Yes, and future value in our case, it is mathematical expectation from F from Payot function. Mathematical expectation from Payot function. And if we write mathematical expectation, it is according to the measure, something measure. It is a risk neutral measure, and in our case, it is the random distribution, the normal measure, normal of the measure of the normal distribution. Okay. So it is like a definition that the fair price is a present value. Present value, it is this factor, present value of the expected payoff of the time of maturity. If it is the continuous time, so you know that this discount factor, we can rewrite like this. Yes, you know this. It is for continuously time, yes? It is for compounding, it is for continuously. And F from Sn. And Sn, we write like the solution of the geometrical Brownian motion. It is solution of the geometrical Brownian motion. But what is f pio function? It is s minus k when s more than k. So we write this like what s minus k. You see, s minus k, and in case when s more than k. So it is just from any d2 minus d2, and we need to define this d2 later. Okay, but why we write integral instead mathematical expectation? Do you remember? Do you remember how we can find mathematical expectation in discrete case? For example, we have x and maybe 1, 2, 3, 6, and we have the probabilities if we through die, for example, yes. And how we can find the mathematical expectation? Lisa, please say.
We need to take value and multiply on the probability and sum up all the values.
Yes, yes. So it is sum of these products, 1 multiplied to 1, 6 plus 2 and so on. It is in discrete case. But if we have continuous case, so it will be the mathematical expectation in this case. It is like sum, yes, x I multiplied pi. By for continuous case, the mathematical expectation, it is what it?
Integral.
Yes, sum in continuous case, it's like integral from minus to plus continuously, and xe and p, it is like a d measure, something like this. Yes. Okay, so it is similar this, and d mu, it is like a measure from normal distribution of normal distribution, you see, and mathematical expectation, it is this pio function, After that, we can write the integral of sum like of difference, like difference of integrals, yes, integrals, and e to the power minus rt, we write under integral, but s before integral. And you see that it will be minus rt plus rt, yes? So minus rt plus rt. And what we see? So we have e to the power sz sigma square root from t, rt minus rt we don't have, minus sigma square t divided by 2, and minus z square divided by 2. And what is interesting that this value, we can write like if we minus before bracket, if we write minus before bracket, so like square of the sum z minus sigma square root from t. And divided by 2, t, and square. So we can rewrite this. Z square divided by 2, it is the last. Yes. And the product distribution the first on the second, it is this, and the square of this, sigma square t, it is this, yes. And after that we can replace this like color. And now we can input new variable u, so it is equals u. So u equals z minus sigma square root from dt. So if we have this new variables, so du dz, d1 in this ways, and if we substitute, you see that we have the next formula. And the integral from this, it is the integral function of normal distribution from d1, and it is from d2. So we have that the fair price for call option, so it's premium for call option, we can find using this formula. We just don't know what is d1 and d2, but it is easy. It is easy. We remember that we have profit only in the case when the market price at the time for maturity more than k. So we would like to find where equals, from which value it is will be. So st equals 0. St, it is we can write like this formula. It is like a geometrical solution of geometrical Brownian motion. Yes, and it's equal k. And from this equation, we need to find z. How we can do this? How we can find solute this equation regarding to z. The first step, we can find logarithm from left and right side, but you see that everything we write on the left side. After that, we need everything z in one side, but everything on the other side. For example, it is on the right, so without minus and everything this. And z equals the other side divided by this coefficient. Yes, divided by this coefficient. So it's just technical moments. So we find d1, d2, and it is the well-known formula Blecker-Scholes or Blecker-Scholes-Mertens. So according to this formula, you can compute the fair price for call option. It is like for premium, where it is cumulative normal distribution, or something it's called like error function. And d1 and d2 we defined on the previous slides too. This formula was published in 1973, and in last year, 2023, we celebrated 50 years from moment when this formula was published, and from the moment when the Chicago Board Option Exchange was opened, and after that, after the publishing, option trading becomes legitimate, not like speculation or gambling. Yes, you understand the value of this formula, because before it was like option trading considered like speculation or gambling, but after publication this formula, option trading becomes legitimate. Black and Scholes, I mentioned that they obtained this formula in other way, and it will be the next lecture. If you would like to find put option, it is very easy because there are put call parity. It's very easy to derive, but okay. So this formula very important in both of finance and in the mathematics. It led to the boom on the option trading and led to an enormous amount of academic work in the theory of the financial mathematics. Yes, this formula and geometrical Brownian motion isn't good, isn't very good, like a very good approximation to security prices, and everybody know this. But this formula is very well like first approximation. And what is the assumption for the Black-Scholes formula? The assumption for the asset, for example, for stocks, it is about riskless rate, that the rate is constant, and it not depends on operation, lending or borrowing, so it's called the risk-free interest rate. The second assumption we can call like a random walk. It means that the log returns of stock prices is a random walk with drift. And we assume that drift and volatility is constant. And the third assumption that the stocks doesn't pay dividends. And there are some assumptions about the market. There is no arbitrage opportunity, so no way to make a riskless profit, riskless. It is possible to borrow and lend any amount, even fractional. So maybe you see that it is assumption doesn't always hold on the practice, but assumptions are assumptions. And it's possible to buy and sell any amount, even fraction of the stock. And the above transaction done incur any fears of costs. So we can consider it our market like frictionless market. And finally, the example. So if we have that volatility 20%, for example, strike price 9, the today price for stock 10, and the time to maturity it is 6 months, so 1/2 of a year, we can compute D1, D2, after that the normal distribution for these parameters, and the call value will be 1.349. So it is like a fair price for premium, and we can to find this on the pattern using GBM and B-S. It's very simple. So I would like, it is very simple. So we import the needed libraries and install GBM, you see. And after that, we write our function like GBM and B-S. It's black shows, and it is the price from today 10. It is the strike price 9. It is the interest rate 5%, and half year it is like in this formula it is in the days. So half year maybe 180 days. I don't know exactly, but okay. And volatility 20%. And after that I write print call price and maybe maybe put price. Maybe I don't like this put price. Okay, and you see that the call price is 1.17. But on the one example, when we where our example this where we computed by yourself, it will be 1.34, but using GBM 1.17. Just we have difference, and I don't know exactly where is we have the more exact result, but what we have. Okay, so that's all for today, and for today we know how we can model riskless asset, risky asset, and how we can the fair price of the derivatives on the modern way. But on the next lecture, we will know how the Black-Scholes have found the fair price, and for this they used riskless portfolio, and it's very interesting, and it is like hedging. It led to constructing a hedging strategy, and so it's very important for us, for investors. Okay, reference, and thank you for your attention. So I need to stop